Hi, I'm Sam. Over here is my co-author Lev, and I want to talk to you about our new temporal prefetcher, Triangel, a high-performance, accurate, timely on-chip temporal prefetcher. So, what actually is a temporal prefetcher? Well, there's been a new generation of what we call these on-chip temporal prefetchers. ARM have one in their commercial chips called CMC, Correlated Miss Chaining. There are very few details about it, but it seems to be incredibly inspired by a set of prefetchers called Triage that they first released at Micro 2019 with authors from ARM and UT Austin. And how this works is that they store what's called a Markov table, which stores address pairs. So let's say that we've got a misstream of A, B, and C. In our Markov table, we have an index A, we still have a target B. So when we see A, we prefetch B. Then when we see B, we prefetch C. It's really not that complicated. Why do we want these? Why do we want to store, then replay this misinformation? Well, it's for things that we can't prefetch any other way, right? So if it's a regular pattern, then your stride prefetcher will pick it up. But if it's weird, if it's linked lists or linked data structures where there's just no other way of predicting it, the only thing you can do is store it and replay it, and that's precisely what these authors do. So this triage paper that appears to have inspired ARM's design, what we have here is that we have a prefetcher that sits at the L2 level. It observes the L2's misses and tagged prefetch hits, i.e. things that were prefetched into the cache by the prefetcher itself when they first accessed. We tell the prefetcher we've done that. What we have is a training table that's indexed by PC, so it splits off the streams for different PCs. That stores the previous address that we've accessed. And then, when we access another address at that same PC, we look into that table and send the thing off to our Markov history table as a pair. Right, so we access dead B0, we last accessed dead beef, we send dead beef, dead B0 to the history table. The Markov table itself is not PC indexed, it's just address pairs, but the point is there's still some PC localization because it gets split up by this history table here. Now, these address pairs are understandably quite a lot of metadata, right? For every miss pair, you've got an index and a tag, and so you need a lot of space to store them. And in Triage, you store those inside the partition of the L3 cache. You steal the L3 cache that you could be using to store data. You dynamically partition between it and actual data and the Markov table to try and do better than just the cache itself. You've got to bear in mind that the address pairs, while they are quite big, they are more dense than the data itself. You can store 16 address index and prefetch pairs inside the Markov partition for every cache line. So that's the basic approach. When we see an address pair, we store off something in the Markov table, and for the address that's just come in, we take a look in the Markov table as well to see if that's got a successor that we can prefetch. And if so, hey presto, we send off a prefetch and bring it into the cache. Now, this is a simple enough concept, but the details are quite a lot more complicated than this. And actually, there were various places that we saw in the original paper where the details were not quite possible to implement or were just slightly ambiguous. There are lots of those that we discuss in the paper in great detail. We don't have time to discuss them today, but please do and go ahead and look at the details in the paper where we show how you can build a really practical version of Triage, and we open source it in Gem 5. Now, the problem with just blindly storing and replaying address pairs is that addresses might not actually repeat, right? And Triage has no way of telling whether the addresses it's storing are going to repeat or not. It may be storing lots of completely pointless metadata, or it may be generating lots of prefetches that are completely incorrect and just generate bad traffic to DRAM. On the flip side, because Triage doesn't know when it's accurate or not, it isn't aggressive enough either. So when it is accurate, it doesn't prefetch far ahead enough to hide all of memory latency. Well, what we ask with Triangel is, can we have the best of both worlds? And I've written in capital letters, yes. Using this special history sampling that we do to work out far into the past whether what we see are repeating patterns and whether we can fit them in the Markov table. We've got these two concepts for that. One is called pattern confidence, which is whether if you store an address pair in the Markov table, would it be likely to produce a correct prefetch? And then we've got reuse confidence, which is it going to be the case that it's likely that if we store this pattern in the L3 cache, we'll actually be able to use it before it gets evicted from the L3 cache's Markov table. If the pattern's too big, you're not going to be able to cover it inside a partition of the L3 cache, right? Also, if we're very confident in the pattern, we can prefetch very, very aggressively far into the future to improve timeliness and just performance. So what we've got here in my example is that, so we've got an address pattern sequence here, where for this PC, we've got XY at this time, then 5 accesses later, we've got XY again. So that's reused in the amount of time that it can be stored in the Markov table, so we increment the reuse confidence. Likewise, the last time we accessed X, we accessed Y. The same is true here. So we've got a good pattern here, so we can do accurate prefetches. For this here, we again access E in short proximity from the last time we accessed E, but this time we access H. So maybe our prefetch to F would be inaccurate, right? But at least the pattern doesn't match. But we still access F in short proximity to where we accessed E. So the prefetch would still be good. So we have to have a slightly more careful definition of pattern confidence than just an exact repeat. We also want to capture when, okay, it may not be an exact sequence, but the prefetch would still be good. And we have a structure called a second chance sampler to help us do that. So this is what Triangel is. This is a lot of different things. We've got our Markov partition in the L3 cache, like in Triage. We've got a training table index PC, just like Triage. But we've got a whole load of other things in here as well. And so if we focus on this stuff on the left-hand side, we've got these new confidence counters that control whether we store things in the Markov table and issue prefetches, and these two samplers called the history sampler and the second chance sampler that tell us for each PC whether there's going to be a good pattern here that we can reliably prefetch and fit in the L3 cache. So this history sampler here, what we do to work out far into the past whether our patterns would be repetitive and thus we could prefetch them, is we sample the entire miss stream from the prefetcher would see. We can't store everything because that would be as big as the L3 cache, and maybe we don't want to do prefetching, right? So we sample, we store a few things all very far into the past using random sampling. Then we check this sampler every time we have a new miss. And if we have the same index, we can check to see if we have the same target as well. If we have a match, then that means that the prefetch would be good, and so we can increase our confidence. On the flip side, if we don't have a match, just like I said, we might have a good prefetch, but we might not. What we do here is we then put the target that we expected to see, rather than the target that we got, into this thing called a second chance sampler, which is pretty simple actually. All it's doing is storing the address we expected, a PC and a timestamp. And if we see this address that we expected to see in close proximity to the address to when we expected to see it, we can still increment our pattern confidence and still issue prefetchers even if we didn't get an exact sequence. It looks complicated, I promise you it's not. Go and read about it. So that's it. That's how we can filter out all of the bad PCs, or maybe every PC entirely if there's no repetitive pattern. But that's not the only thing that Triangel does to improve its timeliness, accuracy, and performance. One of the other big issues with Triage is that it takes up more of the L3 cache than it should. And we have a mechanism to try and trade off the L3 cache with the Markov partition better. Why? What goes wrong with Triage? So Triage, or at least its ISR form, is the second paper in the sequence, uses a Bloom filter that increases the size of the Markov partition while the Markov partition still needs more size. So if there are more misses that the Markov partition could be storing, the Markov partition will grow to store them up to the size of half of the total L3 cache. That's not always the right thing to do, because you're taking away space from the L3 cache that might be more productive than the Markov partition. And when you take away space from the L3 cache, you cause a lot more misses to DRAM, even if your prefetchers are perfectly accurate. And that's not a very good thing to do if you're wanting energy efficiency. So what Triangel does is it uses a set jeweler trained on the filtered output of the samplers, so only on the things that the samplers want to store in the Markov table. And basically what it does, the details are more complicated than this, but basically it stores a full Markov table in a full cache just for 64 random sets in the much larger L3 cache. And it works out from just those two data structures what every possible partition between all Markov table and all cache would be the best joint hit rate. There are lots of other tricks around this to make this all work. There are issues around the fact that the Markov table is a lot more dense than the cache, so you get more value out of the same amount of space, and the fact that you're only storing two possible options and inferring all of the other possible partition options from these. The details are in the paper. It's quite subtle, but it works very effectively to directly trade off the Markov partition for the L3 cache. Something else that we do is high look-ahead prefetching. So the way I explained it and the way Triage does it is that if you see A, they look up A in the Markov table and you get B, so the next access for that PC. The issue here is that each sequential lookup for that Markov table is pretty slow, so we can often fail to hide the massive main memory latency if we're only doing one at a time. What you can do about that is actually offset the index tag pairs. Why do we need to store B when we look up A? Why don't we store C instead? B can be stored at some other index over here, let's say Z or Z for the Americans, and so on, right? B can store D, C can store E. If we do an offset like this, which we can implement using a tiny shift register for each entry in the training table, we can achieve the same level of coverage, but with a lot better timeliness. Something else we can do to improve timeliness, which is a lot more conventional, is increase the degree of the prefetcher. So when we access A over here, what we can do is not just bring in C with the look-ahead optimization as well on the previous slide, but also bring in E, and perhaps even G and I as well. In fact, Triangel, when it knows that it's got a good pattern, if it's more than 5/6 sure that the prefetch is going to repeat, it can do 4 prefetchers every single time it accesses the Markov table. And note that this is therefore a chained lookup, right? We look up A to C to E to G, and then when we see C, we'll do E to G to I. This is a lot of redundant accesses to the Markov table and a lot of redundant prefetchers. So what we do is we add in a little metadata reuse buffer that's basically just a cache that removes a lot of these duplicate lookups. That not only saves you on L3 access energy when you're doing high degree prefetchers, which Triangel does when it's really sure, it also avoids the latency cost with accessing the L3, which also is not cheap. So it makes it more timely again. Right, so in terms of experimental setup, we implemented both Triage, a new implementation of Triage with all of the details that we discussed in the paper, and with a very careful and thorough reading of all of the Triage papers in the series, and our own Triangel in Gem 5. And both of our implementations are open source. You can find them in our paper and on GitHub, and you can extend them and do your own research with them. And what we do is we evaluate this out of order superscalar core here that's sort of vaguely Cortex X2 sized, and we look at the 7 most irregular workloads from Spec CPU 2006, which are the same workloads covered in the original Triage papers. Now, what we find from our evaluation is that Triage itself, at its default degree 1, achieves a 9% performance improvement, and what that costs you is nearly 30% in DRAM traffic. If you increase the degree of Triage to try and make it more timely, you do get a performance increase, but you get a massive DRAM traffic increase, even more than that 30%. You can get more improvements if you add Triangel's new look-ahead optimization, but it's still very high traffic and still not great performance. Triangel achieves a lot higher performance and a lot lower DRAM traffic because it knows when it should be aggressive and it knows when it should switch off. A lot of that is from the samplers, but also some of it is from replacing that bloom filter with the set dueler. You'll note that for workloads like Omnet, what we see is that actually it's all very, very accurate. They are good prefetchers, but they're not worth the cost. So when Triangel with its set dueler can trade off L3 hit rates for Markov table hit rates, it often decides to switch itself up because it decides it just isn't worth the extra cost. So Triangel is of course a lot more accurate because it deliberately tries to optimize for that with its samplers. And it's a lot lower coverage in some cases, again on purpose, because it knows when to switch itself off. But sometimes Triangel is higher coverage than Triage because it can filter out the bad prefetchers and therefore store more of the good prefetchers. Right, so that's a very brief introduction to Triangel. We've got a lot more details in the paper. We've also got a lot more details in some backup slides that you can download from the ISCA website. We've got Lev over here, who you will hopefully see at ISCA. Please do ask him as many difficult questions as you possibly can. Thank you very much for listening, and I hope you find this useful and that you extend it, and then we can have a new generation of fantastic temporal prefetchers. Thank you.